to welcome you this morning to our 10th anniversary annual symposium. The Rutgers Energy Institute is open to all the faculty and students and postdocs across the campuses, and we have about 70 faculty that are within the REI. The REI encompasses at least five schools, and faculty participate just on a voluntary basis. I have lubricants in terms of funds to help develop new programs and new collaborations in terms of postdoc funding or graduate student funding, and those faculty that are in the Institute are eligible to apply. This morning, we'll be discussing one of the most critical issues that face the world going forward, and that is, given the abundance of fossil fuels in the ground and the economics of using those fuels, it's very, very, very difficult to develop alternatives that displace fossil fuels technically as well as economically over the next decade or two, especially in the transportation sector and certain other sectors. At the present, the global production of energy is on the order of about 15 terawatts. And given that the population of the planet will go from about 7 billion today to approximately 9.5 billion by the year 2050, if every family in the world were to use the equivalent of 100 watts, we'd need to generate somewhere in the neighborhood of about 30 terawatts. That's doubling the power production over the next 30 years. And that's a formidable problem. Now, today we're going to be discussing the concepts that have been put forward to how to mitigate the infusion of the atmosphere with carbon that is produced by both direct emissions of methane, for example, or the combustion of fossil fuels that produces carbon dioxide. And both methane and carbon dioxide are greenhouse gases, which means that they absorb infrared radiation, leaving less infrared radiation to leave to space directly, and leading to climate warming. And it's clear that those processes have substantial impact and will have continued substantial impact on the quality of life for us. And there will be economic consequences. The first speaker today is Steve Hamburg. I want to begin by saying that I met Steve just recently, a couple of years ago. We sat together with two of the other speakers, Granger and Jennifer Wilcox, at a National Academy, actually a National Research Council review of geoengineering, and we considered two scenarios. One is removal of carbon dioxide from the atmosphere as one aspect of geoengineering, and some of the speakers will talk about that. And the other was injections of aerosols into the stratosphere to change the albedo of the planet. And I didn't want to include that on today's agenda. So we're not going to discuss that unless Oliver Morton is going to discuss that, and that's up to him. Steve Hamburg is the chief scientist for the Environmental Defense Fund. He got his bachelor's degree at Vassar, and then his PhD was at Yale in the School of Forestry in biogeochemistry. He taught at Brown University for many years before he became the chief scientist for the Environmental Defense Fund. And he's been working for several years on methane emissions. For those of you who are not familiar with this, you may recall just a few weeks ago there was an explosion in downtown New York when people have replumbed gas lines illegally in an old part of old tenements, causing an explosion and 2 deaths. Well, methane leaks are prominent throughout the old aging infrastructures of the cities of the United States. And methane emissions are a huge, huge, huge problem because they're not simple one-point sources. So, and without further ado, where's Steve? There you go. Steve is going to talk about reducing methane emissions and a large climate mitigation opportunity. Thank you.
Thanks very much, Paul. So it's a pleasure to be here. What I want to do is take you on a bit of a journey that I've taken over the last few years, as Paul mentioned, to think about methane and its relationship to climate change. And the opportunity that we seldom get, but I think there are more out there than we realize, to really make a difference quickly, to have an impact, and to resolve an issue rather than just to wring our hands. As when I was an academic, we spent too much time thinking about what we couldn't do rather than showing what we could do. So this is going to be a story about how we have tried to bring the scientific community together over the span of just a couple years to answer some key questions to allow some real fundamental changes in policy so that we can get actually tangible results. So I'm going to start and talk a little bit about methane, and I want to just point out a few characteristics of it relative to being a climate pollutant. So if we think about CO2 and methane and how it reacts in the atmosphere once it's put up, CO2 between the oceans and the terrestrial biosphere gets taken up, but the remainder of the I guess I don't have a pointer, the remainder of the CO2 after that initial pulse of absorption in the oceans basically sticks around for a very long period of time, which is our big challenge. It's a long-lived climate pollutant. Methane, by contrast, when we put it up into the atmosphere, chemically reacts and degrades so that after 50 years, most of it's gone. So that's the good news. So we have a pollutant that's long-lived and one that's short-lived. The challenge with methane is that over the short term, it's much more potent as a greenhouse gas than is CO2. So it's roughly 80 times more effective. So the challenge is in the short term, methane is affecting our climate when we emit it to the atmosphere much more so than is CO2 relative to the amount that we put up. And in fact, today, 1/4 of the net impact, net radiative forcing caused by human greenhouse gas emissions is 1/4 is caused by methane. So 1/4 of the climate change you're experiencing today is a result of methane that's in the atmosphere from human activities. So it's a big deal, and we need to do something about it. So just to think a little bit about the global methane budget, we can think about half of it roughly is natural processes, but the other half is human activities. And so the question is, how can we reduce those excess methane emissions from human activities? I'm going to focus largely on this fossil fuel piece of the global budget. I'll talk a little bit about the US. So we're going to start there. Why do we start there? Because it turns out, I'll give you one of the punchlines. We already know how to reduce those emissions dramatically. The answers are in hand. We just need to apply them. If we look at just the relative global, this is the total amount of methane. This is, if you can't read it, agriculture, oil, natural gas, and oil production. This one is waste and coal, etc. So the dominant is agriculture, and I won't talk about that, but we're also working on rice farming and ruminant emissions, but I will focus on the second most important, oil and gas. And if we look at the US and we look at natural gas and oil, we see it's actually proportionally more important. As a single source, it's the largest source of methane of the US methane budget. So it's a big deal. And if we think about how important it is, and you see the numbers and they change a little bit, if we think about it, you'll hear somewhere between 9 and 13% of the net greenhouse gases in the US are caused by methane. But the challenge is that we tend to use a metric that's very problematic, which is CO2e. That's science, unfortunately, scientists made a decision that wasn't a science decision, to say all we care about is the impacts over the first 100 years. Well, that's sort of saying that my life and my daughter's life is discounted for my grandchildren's life. Well, I don't think that's actually true. They're both important. And so what we need to think about is, we need to think about 100 years and 200 years, but we also need to think about the short term. We need to do both. We need to, what I refer to as the and proposition. We need to worry about the climate impacts over the short term. I'm an ecologist by training. I care about the rate of change, because that's what's going to determine the impacts on the ecosystems I study. And in fact, since the time of my initial plots that I put in for my dissertation work, I can actually directly see in the forests of New Hampshire the effects of climate change. I can take you out in the field and I can show you how climate change is manifesting in those forests. That's determined by the short-term rates. That's not instead of the long-term. We've got to do both. So we need to think about this problem a little differently, not just as at 100 years. We need to think about both. So if we think about that, there was a recent paper about a year ago by a group out of Harvard, Shoemaker et al., that looked at what are the potential implications of this and proposition. And if we do, in this case, a fairly not too aggressive climate reference case, it's not business as usual, we can look at temperature change over the next couple hundred years. And then if we just were to mitigate short-lived forcers, not getting rid of all of them, but as aggressively as we could imagine, what you see is you actually can slow the rate of warming in the near term. These are short-lived forcers. We get rid of them. The effect of doing that reduction is restricted to the next few decades. And then, of course, it picks back up and basically follows the line, but with this gap as a result of that. If we do just CO2 in their modeling and their set of assumptions, you have very little effect over the short term, and of course you have a big effect over the total amount of warming that happens over the long term. As a society, we need to do both. We care about both. We need to think about this as CO2 and short-lived forcers, because that's the only trajectory that we can see where we're going to reduce the risk to society, give ourselves the room to adapt to a low-carbon economy, recognizing the resistance in the infrastructure that's developed. So the bottom line is we need to use the and proposition. We need to do both, realize that we've got to reduce the rate of change and the magnitude of change. And the only way we can do that is by having policies that focus on two climate goals in the parallel. Not an or, an and. We need to do both. To do that, we needed to figure out, going the wrong way. We needed to figure out policies on this. We were, of course, working as a society on CO2. We have the clean power plant rules that are coming into effect. And so we focused a lot, because there was an absence, on the short-lived climate pollutants. And the challenge is, this is an old, most of you in the room are not old enough to remember, but it's a New Yorker cartoon, a Sidney Harris cartoon that I love, which is, as you can see, there's an equation on both sides. In the middle it says, then a miracle occurs. I think we need to be a little more specific here. Well, the problem was, I could talk about short-lived climate pollutants. The problem was there was no data. I like to describe it 3 or 4 years ago as a he said, she said, they said, we said problem. Everybody had their data, everybody had their opinion, and they could defend it, and we couldn't resolve it. So we set out to try and change that. The first thing we did was develop some better analytics. Sorry, it's a little washed out here, this top curve, but we developed what we call the technology warming potential concept, which was if you fuel switch, if you go from fuel A to fuel B, what's the relative impact on net radiative forcing over time? Not at 20 years, not at 100 years, over time. And then what, in this case, we're looking at methane, how, if we're going from coal to natural gas, how much methane could leak, which is this potent short-lived forcer, such that it would undermine the carbon advantage in the case of coal to natural gas. Coal production, electrical production would be roughly twice as much carbon dioxide emissions. And what you see is that about 2.7% methane leak, if you do that shift on a fleet basis, if your leak rate across the entire supply chain is less than 2.7%, you're getting climate benefits immediately. And of course, because methane is a short-lived climate pollutant, the benefits grow over time, or the leak rate would grow. So if you decide, well, I need to have benefits after 40 years, it's about 4%, et cetera. And you could do that for gas cars going to natural gas or diesel trucks as well. You can figure out what these rates are. This is a tool that simply allowed you to understand the implications on climate of using the fuel switching. There was a very active debate about whether we should switch fuels. That started with the analytical framework. We still didn't have the data. So so to think about what data we needed, this is a graphic from a paper Brandt et al. Appeared about a year ago in Science. Just looking at it, we think about the supply chain. We produce natural gas at a well. It goes through production, the well drilling, the completion, the production, the processing, the transportation, and the use in your house. These were the numbers. The percent leakage is estimated by EPA. These are just some of the studies that have been done to look at this. The bottom line is there really wasn't sufficient data to really effectively characterize that. The study, I'll come back to the study in a second. So when we think about it, how much methane was leaking relative to what EPA thought it was leaking? A paper by Miller et al. In 2013 that used tower data suggested that the national budget was about 50% off. It was too low. There was 50% more emissions from the natural gas supply chain, in this case also from agriculture, than was estimated. Brandt et al. Only looked at the natural gas supply chain, or the oil as well, and came up with an average of 50% as well. But again, that's nice. You publish a paper and you say it's off. But where is it leaking? How much is it leaking? And how do we reduce it? So that's what we set out to do, figure that out. So we did a series of studies. We brought in more than 100 academic scientists, as well as from universities and some from corporations, set up 16 studies that I'll describe in a minute, using as many techniques as we possibly could. What we wanted to do is we had our little Air Force, we had many planes in the air, we had tower data, we wanted people on the ground making measurements. The idea was, let the very strength of academic research be brought to bear in a short period of time to answer these critical, societally important questions. But the distinction was we asked everyone to do their work quickly. Do it in a year. Make your measurements in a year. Not in 2 years, not 3 years, not 5 years, not 10 years. Do it quickly. And in so doing, by bringing this community together, we could organize a study that had never been undertaken before, of a scale that we looked at the entire supply chain, all the way from production that I just described, all the way to a limited degree end use. Really cut it off here. And we got all these different teams, different papers. There's going to be roughly 30 or 35 papers. The majority are already accepted or in print. The rest, those that have been accepted, most of them will be out later this month. And we're finishing up. Most of them, the green have been published, the yellow are in press or in review, and the red are the ones that we have yet to submit. The key here is organizing the academic community, the best researchers in the country, and focusing them on a real problem using the best techniques. And as my colleague Steve McCall at Princeton likes to say, get everyone in a room and nobody trusts anyone else, so they look over each other's shoulder and they test each other's results. And that result, we had everyone, we used as many methods. So we had top-down people flying airplanes, people measuring on the ground, challenging each other to what they found. The most healthy sort of approach to research, but very targeted and focused and coordinated so that each one built up against the next so that we could build a big picture in a record of short period of time. Now, EDF, we do not take corporate funding, but we needed the support of corporations to get access to a lot of these facilities. So we raised independent money to support the bulk of the research. The corporations, we asked for partners who were willing to give access and participate. They provided research funding to the academics as well, though a minority share. And together, we got unprecedented amounts of data. Like on the production study, here, the 28, I believe it was, completions that they measured the gas emissions from those. Nobody had ever made those measurements before. I'm going to focus now on a specific, before I do that, sorry. One of the key characteristics of the results we saw from across these studies was the distribution. This is a cumulative emissions curve. So of all of you, look at a population of measurements, the first sample is here down to the last sample there, the first emission to the total emissions. What you see in a curve like this is just a series of different studies. This one was one done before. This is stuff that we were involved with, and this is one that we're just about to release. You look at it and you find that roughly a third of the sites have no emissions. People are doing it. They know how to do it well. The industry can do it. You can look time and time again and find a drill pad, transformation, gathering lines, processing, and it's working well. But you also see you got these sites up here where just a few spots are emitting lots. In economic terms, we refer to this as a fat tail. There's a distribution where a large percentage of the emissions come from a limited number of sources. So in these data particularly, you can 10 or 20% of the sites account for 60% of the reductions. Now, the important distinction here is it's not that those 10 or 20% of sites is fixed. It's not like somebody broke it and it's been sitting broken. It may be changing over time where those are. But the good news is a lot of people know how to do it well, and we have a relatively limited number of sources to be able to reduce those emissions. So we've got a good news story here. We know how to fix it. It represents an important source of emissions, and the number of places we have to fix are relatively discrete. Not none, but they're not overwhelming. So we wanted to take this with the community that we were working with and really understand how this all came together. So in October of 2013, with the support from the Sloan Foundation, we assembled as many teams that wanted to come and play in a single sandbox, the Barnett region of Texas. We had top-down, we had airplanes, we had 4 teams with airplanes. We had people driving cars. We had people going to cross the supply chain, all in one place, all at one period of time, in order to compare and contrast and really understand. Why? Because if you looked at the literature until this point in time, what did we see? The top-down numbers uniformly were higher than the bottom-up inventory. If you take all the pieces at the bottom and you add them up, the numbers don't add up to what you see when you go to the atmosphere. Well, you can imagine the conversation that's happening. People who think a low number is good say those data are better. People who think a high number is good say those data are better. So we're not getting the resolution. So we developed this campaign, which we call the Barnett Campaign, which the papers will largely be published this month. That involved bottom-up measurements. Here you see an individual making measurements. They've got a kind of nozzle arrangement from an individual flange. Or here you see this is the University of Houston van, but we had Aerodyne's van. These are highly instrumented trucks that are driving and making a series of measurements, allowing us to really get the detailed data from the Barnett in this period. We had a series of university teams as well as private company teams, but with scientific experts, making a whole series of measurements from a whole different sources. Because we can't just look at natural gas supply chain and the oil. We had to look at landfills, we had to look at cows, we had to look at all the possible sources so we could make sure we understood what was going on. The key there is one of the staff, EDS staff, then took all the data, scraped all the data they could find from all the different sources and built a spatially resolved inventory. What was where? This doesn't exist. Nobody had this. And you could verify it. We have these wonderful tools now. You could look on the ground and actually verify where everything was. Because in some cases, those inventories have data that are wrong, or it's misplaced, or there's missing. So he built this very detailed database that allowed us then to populate it. And you could create these kinds of images. This is total methane emissions from 25 counties, and this is Fort Worth. Dallas-Fort Worth is over here, the central part of Texas. And the Barnett, I should have mentioned, is where hydraulic fracturing in the modern gas boom started. This was the place that first used at scale horizontal drilling with hydraulic fracturing, which really created the change in our fossil fuel economy that we're seeing today. This is the methane emissions from just thermogenic, so those geologic sources. This is biogenic sources, and here you get a sense of where that is in Texas. And I just wanted to show you as an illustration of the data, and I apologize I can't show you more details. They'll be out later this month, as well as a synthesis we're working on. But this is a log scale of the proportion of loss from individual well sites, production sites. There are multiple wells often on a production site. This is 100%, this is 0 log scale. And then this is the log scale of production. Notice here, 100%. What does this point mean? That means at that well site, 100% of the production of that well was being emitted to the atmosphere. That is 15%. Everything above this line is 10%, is more than 10% of the production. And notice over here, these are high producing wells that are putting out large amounts of methane. So one of the work of a postdoc in my group is we really started to bring this. Nobody had ever put this data together to look at this so we could actually figure out what that fat tail looks like. Where are those sites? What's going wrong? Certainly, there isn't a whole lot of sense, even to the operator, to operating a well that you're basically operating and emitting 100%. Now, that's rare, but it still happened. All the production's going up. Now, that's a very small well, so it's not an absolute quantity, but even the wells down here at 10%, you don't need to be giving 10% of your production away. And we have lots more of this data that we'll be releasing soon. But the other thing we wanted to do is do top-down. What do the emissions look like when we go up into the atmosphere and see the integration of all of this? Does it match? Here's Bob Harris, who's a senior contributing scientist at EDF. He came to EDF after retiring as the president of the Houston Advanced Research Center, a longtime methane geochemist. Steve Connolly flying a plane. This is actually data from the Denver-Julesburg project from Patron et al., but we produce similar types of measurements flying over the entire region that will be again released later this month. So we can look at large emissions from this total area. We can find difficult sources that can identify them, and we can put this together. We again had multiple universities working together with research teams doing compatibly, contrasting, I should say, but compatible research. I did have to say that I worried at night. I might be the chief scientist in NGO, but the notion that we had all these planes in the air looking at similar things at a similar time is a little bit nerve-wracking to make sure that they're coordinating well, because the last thing we need is a problem. And they are. They're all professionals. This is just an example of the flights they did. This was the first time these measurements had been made. These are 8 flights over the same region. No one had ever done it that often. Sometimes you go up and the weather conditions aren't optimal, so you lose some flights. So we could get repeat measures from across the region to compare. And then these are just an indication of the summary results across different studies. So I mentioned the studies that Miller et al. Here, and these are different inventories that you can compare it to. These different shapes represent different inventories. This number here is the ratio of the top down to the bottom up. So some of the comparisons, the inventories are 5 times off. The top down is 5 times higher than the inventory. Some are 2 or 3. Here's our study. And these are actually just preliminary tentative results. They're changing slightly in what will be published. And I'll give you a hint, they're getting closer to 1. So the point, for the first time in the literature, we can actually balance the data. We can explain where it's coming from, how much is coming, and we can do it multiple ways and get the same result. This is incredibly powerful because we can now take action to reduce those emissions. I want to just briefly, Paul talked about the urban infrastructure, a project that we announced last July, a project we've been doing jointly with Google Earth, adapting street view cars to making scientific measurements. So we've been driving these cars around the country, mapping, I should say Google's driving the cars, we're processing the data and doing the science. Mapping the United States, cities and their methane leaks. If you go to edf.org, you can see these maps. You can go zoom in. This is Boston, and this is Indianapolis. Every dot represents a leak, identified and verified leak. So the darker the color, the bigger the leak. What we were able to do is quantify these leaks. For the first time, we have the algorithms to allow us to drive the Google car at street traffic and turn that into where the leak is and how big the leak is, as a small, medium, and large category. Indianapolis replaced its pipes. Boston has not. Now, the majority of the pipes have been replaced in the country, but our old cities, like where I live in Providence, literally on my walk to the train station to come here, I had to go through a lot of construction because they were digging up the 130-year-old cast iron natural gas pipes to replace them. Rhode Island had the highest percentage of old pipes. They now have an accelerated pipeline replacement program. The pipe in front of my house was replaced 3 years ago. They're working on my neighborhood, which is one of the older neighborhoods in the city. The goal here was to present data to society to make an informed decision. One of the things we worked really hard on in producing these maps was ensuring that people understood what they did say and what they didn't say. I have a social psychologist on my staff, Rainer Romero, who did a lot of experimentation to find out how do people react to this. We want to produce concern, but not fear. These are not explosive leaks. These have been graded by the utility. They've been rated to be ones that are concern from the environment side, but don't need to be fixed based on rules right away. But they still add up to a lot of gas, a lot of methane that's leaking. We need to do something about it. We wanted to give the tools to the utility, the PUC, and the public. These data were never transparent before. They were behind closed doors. You couldn't see this data. Our goal is to make it transparent to everyone. So if you live in that community, you can say, why aren't you doing something? In the case of communities where there isn't accelerated pipeline replacement, or how are you prioritizing repairs to make sure you repair the biggest leaks? They've never known which leaks were the biggest. They simply knew whether it was a grade 1, 2, or 3. Grade 1, you fixed immediately. Grade 2, you got to fix fairly quickly. Grade 3, you put it on a watch list. These are grade 3 leaks. They're watching them. We need them to fix them. Indianapolis made the commitment to replace their old pipes with plastic. They have a resulting minimal number of leaks. And the data shows something quite dramatic. So for Boston and Staten Island, which we released last summer, we've just released 2 more cities, and we're about to release several more, so we'll have about 10 cities posted pretty soon. So if we look at this, is again a cumulative emissions curve versus the rate, and I apologize, I should have fixed this. This is emissions rate liters per minute. The scale here is printed on top. So if we take a Staten Island, 10% of the leaks account for roughly 35% of the emissions. In Boston, 14% account for roughly 45% of the emissions. You get a factor of 3 higher. So if you just fix those 10 or 14%, the top leakers, you'll get 3 times leverage over if you randomly fix them, which is what they do now. So that you can now have a new policy procedure that is actually getting tested by a dozen utilities to use this technique in order to improve their methodology. So even using existing funds, we can greatly reduce emissions by simply prioritizing appropriately. This data never existed because no one had developed the algorithms to turn this into a quantification process. We did that by collaborating with Colorado State University and my science team at EDF. I want to talk about one other thing we're doing, which is to try and bring detectors and accelerate the technology changes necessary to make sure that people know, the operators know when they have a problem. I recently had, in the middle of the night, my smoke alarm went off in my house. I ran around like an idiot. My wife was the cool one, and discovered that in fact our basement was filling up with smoke. Turns out there was a small fire from a defective light fixture. We were able to solve it quickly, but because the door was closed, we could have had, the whole house could have gone up had we not had that smoke detector. So we solved it, wasn't a big deal. We have the same thing with a carbon monoxide detector. Why aren't we applying that in the industrial setting? We need a methane detector that tells the operator when you have an upset, just like you do at home. So we believed that the technology was mature that would allow that, but the technology developers didn't know the need and the operators didn't know the potential. So what we created was bring them together. So we got a series of companies that produce natural gas to basically say they will buy it if you can produce it. And we went out and found the innovative community. We put out an RFP, we paid them no money and said there's a market if you can produce it. And we're in the second phase of testing. These are our finalists. We had 20 applicants down selected, did a set of lab tests on the technology in order to select the ones that could win. They're now in the field testing, and we're simply making the marriage with the goal of having a cheap methane detector equivalent to your smoke alarm that can be put in the field so people don't have to wait long periods of time before they discover there's a leak. This is just some of the innovators. They come from around the world, from big companies to academic labs that are trying to compete for what could be a very large market for putting these things in place. Just want to say that we do, again, our goal is to reduce these emissions. We believe that with the current announcement by the federal government, based on this work and others, the President and the White House has announced a commitment to reduce emissions by 40 to 45% from the natural gas supply chain, and they are going to be proposing rules to move on that this summer. So we could empower science, understanding the climate cycle, the carbon cycle. We could then bring the science to bear to affect a policy outcome that's going to help everyone. Thank you very much.
The fat tail business on the well pads.
Not just the well pads. So the fat tail applies across the supply chain.
Right. So what I think I heard you say about that slide about the well pads was that there were a reasonable number, 30% or so, that were basically doing it right and doing no emissions, which implies that those were individual well pads that were being well run. On the high end, what I think I heard you say is that the bad ones vary around from place to place.
Correct.
Is that what you meant to say? And
yes.
What's going on there?
So unfortunately, we haven't finished analyzing all the data. We're working on a synthesis right now. So a couple things. So some are going to be fixed. Something's broken and it stays broken for a period of time. But they also can be a short-term phenomena. Something happens, pressure builds, it releases where it shouldn't. So that may happen in place A now and place B later. Something may break in some new place. So we can't just focus on the 20%. We got to have a monitor in all of them. But the good news is you just need to know when it breaks. We got to learn from that. And we're seeing that happening in the industry. So if we start better understanding when things break and why, we know that company X's valve breaks twice as often as company Y's. Well, you're going to buy company Y's going forward. And so that's the goal, is to provide the knowledge, and the companies are starting to do that. They're starting to build their own records so they can start to learn and say, look, it's a lot cheaper for us if we can anticipate a problem than having to react to a problem. And we can react better if we know it happened. And that's the idea of the sensors.
A lot of dramatic data. Can you talk about what was the dollar value of that being lost every year? You didn't mention it, but it sounds like a lot.
I apologize. We have done that calculation. It is a large number, and I don't remember the accurate, because I've been working internationally, and I'm in my head right now, I'm mixing up the international number and the domestic number. But it's a big number. But it really, I think the most important is how do you use that value to affect the economic propositions so that companies are able to make that change. So I didn't show the data. There was a study by ICF International that we commissioned that showed that 40%, I think that's quite conservative, but that's their number, 40% of the emissions could be reduced for 1 penny 1,000 cubic feet. So that's about 1/3 to 1/4% cost to reduce those emissions. And that's aggregating it. Now, obviously the local infrastructure pipe replacement is very expensive. So even though you're losing it there, that's a different proposition. But there we do have issues also of safety. We also have just a commitment. We shouldn't do things that are unhealthy. And the key there on the local pipes, which I didn't mention, is clearly safety, safety, safety first. We don't want explosions. But we need to add and environment. So we can deliver the gas and we can deliver it with optimal outcomes. We can do both. We don't have to pick one over the other.
Speaking of carbon monoxide, are you concerned with that at all? Because it degrades the OH radicals that break down methane in the atmosphere. So carbon monoxide actually makes methane last longer in the atmosphere.
We have not focused on that. I'll defer. I'm sure there are others in the room who are better atmospheric chemists. I'm a terrestrial biogeochemist to look at how much the relative emissions of carbon monoxide are affecting those decay curves. Yeah. I would suspect it's relatively small and localized. Obviously, pollution, you don't want carbon monoxide because you're getting incomplete combustion anyway, so you want to minimize that through good operation of your plants, but I don't know enough about the differential rates of emissions.
Sure.
Okay, thank you very much. Thank you.